today. What do you say, Juliet? Ruby Rose. Oh my goodness. So you want to take her? Sorry. Okay. Hey, well, welcome back. Hope everybody's doing okay. Where we ended last time, we were on chapter 10. And specifically, we were talking about the types of reactions. Okay? And there's 6 types of reactions. That's what this whole chapter is about, chemical reactions. Of all the chemical reactions that occur out there, that's all we got, 6 types. The first type, this is the slide we ended up, is what we call a combination reaction. Now, in this scenario, what you really actually have the majority of the time is you have 2 elements coming together to form a compound. So we got 2 different elements. So in this example, this is a generic equation where we have A plus B to give us AB, whatever AB may be. Classic example of that would be water, the formation of water, where we have hydrogen, and in fact, let me write that in there, where we have hydrogen gas reacting with oxygen, okay, to give us H2O, good old-fashioned water. Okay, that's a good example. Now, the other type, and that's called a combination. Just like the term says, we are combining elements. The other type is the opposite of the decombination reaction, and that is called the decomposition, where we're taking a compound, ABC here, whatever it may be, we're doing something to it, we're breaking it back into the elements. And we can also use as an example is the opposite of the example we just did. And this is called the electrolysis of water, where you can take water and you can hit it with some electricity and you break it back down into the elements of hydrogen and oxygen. Okay, so a decomposition reaction is basically the opposite of a combination reaction. A combustion reaction, just like the term states, combustion, we are burning something, okay? That being the case, we need as a reactant oxygen. So oxygen will always be a reactant, okay? Now, with respect to combustion reactants for Chem 130, we are only going to deal with what are called hydrocarbons. And it's denoted here by this general formula of carbon and hydrogen, and X being a number and Y being a number, okay? And so hydrocarbons are simply any compound that is made up of nothing but carbon and hydrogen. A good example of this would be like methane. In fact, the smallest number X could be is 1, and the smallest number Y could be is 4. And that is the smallest hydrocarbon called methane. But you have things like, you're all familiar with propane, where you're out there cooking, frying up your hamburgers using the propane tank. Things like butane, if you're lighting up your Bic, that contains butane in there, which are basically all hydrocarbons. And acetylene, another example would be acetylene that is used to, cut metal. Acetylene is very, very powerful gas, but they're all hydrocarbons. Now, with that being said, the only products you have to be concerned about when it comes to combustion of hydrocarbons are 2 products, and that is carbon dioxide and water, okay? That's it. So it's the only product. So for combustion of hydrocarbons, you need oxygen as a reactant. And the only two products you have to be concerned about is carbon dioxide and water. Yes, we combust hydrocarbons in our engine. Yes, we create carbon monoxide, which is a poisonous gas. But that is because engines that we use and the injection of the oxygen and so forth is not very efficient. It's due to the lack of efficiency of our combustion engines. Therefore, we end up with carbon monoxide as a side product, okay? But for us at Chem 130, combustion of hydrocarbons requires oxygen, and the only products are carbon dioxide and water. Okay, second type. This one we talked about when we dealt with the acid-base reaction chapter, okay? Now, the reaction of an acid, and that is by definition, recall the definition of an acid, is any molecule or compound that produces a proton, that is the H+, produces a proton. So normally what we talked about was these organic acids like hydrochloric acid, nitric acid, carbonic acid, so on and so forth. So they produce a proton, and 9 times out of 10, when they are written out, you normally see the hydrogen written first. That's a good indicator that you're dealing with an acid, 90% of the time. With the exception of water. Notice water, the way it's written, H2O. Hydrogen is written first. Well, the fact that it's H2O, it's not an acid. Okay, it can act like an acid, but it's not an acid. Okay, so everything else, and normally A is some anion, the sulfate, the nitrate ion, anion, any of the halides. Now, with respect to the base, by definition, is any compound, and the majority of the time, we are dealing with ionic compounds that have the hydroxy polyatomic ion. Okay, so by definition, anything that produces a hydroxide is a base. So in this case, the metal can be anything. This could be sodium, any metal, sodium hydroxide, potassium hydroxide, you know, any type of metal, but the hydroxide's there. Now, when the hydroxide that has a negative charge and the proton, which has a positive charge combine, the water that you always get is, the product that you always get is water, okay? That's how you neutralize. So you may even try this at home. If you have a little bit of baking soda, which is the base, a little bit of vinegar, which is the acid, it's the acetic acid. You put them together, you get a reaction, and bubbles start to form. Okay, that is the neutralization reaction. You are neutralizing the acid in the base. Okay. You can also do that if you ever get any acid in your battery, your vehicle, you crack the battery and there's acid. Hit it with some baking soda. That will neutralize the acid that's coming from your battery. All right, so the product you always get is water because you have neutralized the acid component and neutralized the basic component, okay? And the other product would be the corresponding salt, with depending on what M and A is. And so you end up with Ma, okay? And that is the combination of the M from the hydroxide, which is the metal, and the A from the acid, which is the anion. Okay, the metal has a positive charge, the anion has a negative charge. They combine to form the salt, the ionic compound. Okay, so that is an acid-base reaction, aka neutralization reaction. Where are we at? Okay. Now, the next type, which is the 5th type, we call that a single replacement reaction. Let me clear up the marks here a little bit. Okay. And here, this is what happens. We have a metal in elemental form. Okay. it reacts with another metal. Let me change the color. That is in ionic form. So AX is an ionic compound of some sort. Now, what happens if reaction proceeds, and I'll explain to you how we can predict whether the reaction proceeds, is the two metals exchange position. So now you have created the elemental A metal, whatever that may be, okay, because it started off as an ionic compound as AX, and now is simply A, the element. And the M, which started off as the metal, now is in an ionic form. Let me change the color, make sure we're still in the same consistent color. M now is in the ionic form. So we replace the metal, okay, that was in ionic form with the new metal that was in elemental form. Now, how do we determine whether this type of reaction proceeds? Well, I'm glad you asked. We go back to the periodic table and we utilize the what is called the activity series. It is right above the solubility table. Okay, it is right there. Let me highlight it so we all know where we're at. This is the activity series. Okay, and what this is, and you'll be given homework or activity problems dealing with give an example of a single replacement reaction. Use the metals that we have here. Okay, if you use other reactions, it's good that you go out there and search things, but if you use something other than what we offered, then at least tell us where you got the information. I have no problem with you guys going out there and getting information as long as it's correct and good information. But if you use another example of a single replacement reaction other than the metals we deal with, that's fine. But you know, tell us where you got it so we can verify. So here we have the activity series. Now, how does this work? All right, so let me change this. What this is telling you is this: the ones that are underlined, starting with lithium and all the way to sodium, they're in bold and they are underlined. Those are very reactive metals. They simply touch water and they react quite drastically. In fact, if you were to take sodium metal and dump it into water, you would have an explosion because the reaction is so rapid. You produce the metal hydroxide and you produce hydrogen gas and a ton of heat. And that heat ignites the hydrogen gas and you get a nice little explosion, okay? And so those metals that are underlined are very reactive. Now, the most reactive metal that we have is lithium. So lithium is more reactive than potassium, barium is more reactive than strontium, so on and so forth. And it goes to the end of the list that demonstrates that gold is the least reactive of all these metals in the series. Gold is very unreactive. It can last underground, buried for thousands of years, and when you take it out, it's just as shiny as it was when it was put into that soil years and years ago, because it's so unreactive. You can get it to react. Don't get me wrong that it's not totally unreactive, but to get it to react, the conditions are very aggressive. Now, all these series is relative to hydrogen. You notice hydrogen sitting there. So this hydrogen reactivity the activity of metals are relative to hydrogen. Now, hydrogen is either in the form of H2 or in the form of water. The point being is if these metals were more reactive than hydrogen, then they're below as far as reactivity with respect to hydrogen. All right, so how do we determine whether something is reactive? Well, we're going to ask two questions. We're going to do some examples of that in a bit. Let me get back to the table. And so we'll talk specifically about examples for single replacement using the activity series. Now, the next type is called a double replacement reaction. And notice the first one had a single replacement here. This was called the double replacement. Now, let me make sure I color coded. Notice we have written here in generic form M1. Let's make sure. I got M1 combined with X. M1 could be any metal, and X could be any anion. Okay? Well, it recombines with M2's partners, and now you have M1Y. Okay? With respect to the other reactant, we have M2Y that now has changed partners with M1X, and now we have M2X. Okay? So basically, the anions and the cations exchange. Now, how do we determine whether a reaction proceeds? Well, in this scenario, what we do, first point about double replacement reactions. The reactants are soluble in this solution, which is an aqueous solution. So the reactants are nice, clear solutions. What happens is you take them and you put them together, and then something happens. If they remain clear, then nothing happened. There's no reaction. But if it gets cloudy, that means a reaction happened. Now, how do we determine that? Well, we go back to the periodic table again, and this time we utilize the solubility rules. Okay, we talked about the solubility rules. We'll go over them again here in a bit. On the left column is the soluble, and the right column is the insoluble. Okay, now if one of the products, one of the new products is insoluble, that means a reaction proceeded, and you get a precipitate, you get a cloudy solution. Okay, because one of the products is not very soluble in an aqueous solution, therefore reaction proceeded. If both products are soluble based on the solubility rules, then no reaction occurred. Okay, so here, very simple, partners got exchanged. You start off with two ionic compounds, two ionic reactants. You exchange the cations and the anions, then you look to see, look up the solubility of the new products and determine whether they're soluble or not. If one of them is, then you got a positive reaction. If both products are soluble, then there's no, we write it down as NR or no reaction. Okay. All right. So let's run through some examples, specific examples of these 6 types of reactions. Okay. The first one here, we have phosphorus and we have oxygen. Note that there are 2 elements, just like the combination reaction. Okay, we got 2 elements combining to form a compound. In this case, diphosphorus tetroxide. Okay, so it's a classic example, a good example of a combination reaction. A decomposition reaction, if you go back to the formula, general formulas, you'll see you have a compound, and you do something to the compound to generate the elements that compound was made from. Here we have iron 3 oxide, which is AKA rust. A little bit of heat, actually quite a bit of heat actually, breaks the iron 3 oxide apart, and when you end up with oxygen that it goes away, because it's a gas, and iron. So you create elemental iron and elemental oxygen. Typical example of a decomposition reaction. Okay, that one is balanced, a balanced chemical reaction. Okay, combustion reaction. Okay, now with respect to balancing these reactions with the combination reaction, the decomposition reactions, generally it's kind of a trial and error process. you note to see how many elements we have of each, and we start adding numbers, and we go work back and forth from reactant to product, product to reactant, until we find the appropriate number to balance that chemical reaction. Okay, in this case, 2 iron, 3 oxides require 4 irons and 3 oxygens. That's balance. Okay, we have 6 oxygens as reactants, 6 oxygens as products, 4 irons on both sides, so we get a balanced chemical reaction. Unfortunately, for these type of reactions, it's basically trial and error. However, when we get to combustion reactions, not so much. We have a little technique to tell you how to balance it, and I'll share that with you here in a second. Here they're asking you to write a combustion reaction for propane gas, and they give you the formula. And if you look at the formula, nothing but carbon and hydrogen, therefore a hydrocarbon, okay? It's a combustion reaction, so a reactant you need is oxygen. Remembering that oxygen is diatomic, so the formula for oxygen is AO2. And then remembering that for any combustion reaction of a hydrocarbon, the only 2 products are carbon dioxide and water. With that information, you can write the formula for the combustion of, in this case, propane. That is the formula for propane. So next time you're out there cooking your hamburger, think of C3H8, okay? That's propane. Now, we have a procedure for balancing combustion reactions. Okay, and then step number 1 is you balance the carbons first. Okay, then step number 2, you balance the hydrogens. And then finally, number 3, you balance the oxygens. Okay, so that's the order of balancing any hydrocarbon reaction. So let me go through that real quick. Okay, carbons first, followed by hydrogens, followed by the oxygen. So let's take a look at this reaction we got here. Okay, so we have 3 carbons on the reactant side, 3 in propane, but we only have 1 on the product side, 1 in carbon dioxide. So what we do is we simply put a 3, and let me make sure I got it up. Move it over a little bit. Okay. We put a 3 in front of carbon dioxide. Okay. So that balances our carbons. We got 3 carbons on the right side, 3 on the left side. The next step, we balance the hydrogens. Well, we look at the reactant side, we see that we got 8 hydrogens in propane. And we only have 2 hydrogens in water. So to balance the hydrogens, we simply put a 4 in front of water. Okay, does that make sense right now up to this point? So go double check. We still got 3 carbons on both sides. Now we have 8 hydrogens on the reactant side and 8 hydrogens in the product side. So now the hydrogens are balanced, the carbons are balanced. We look at the oxygens, okay? Reactant side, we have only 2 oxygens. Product side, we have 6 oxygens coming from carbon dioxide and 4 coming from water. That means there's a total of 10 oxygens on the product side. Okay, well, to make things balanced, all we got to do is put a 5 in front of oxygen. Okay, by putting a 5 there, now we have 10 oxygen atoms on the reactant side and 10 on the product side. The result is now, let me put the next equation there with the numbers a little bit clearer. You can see that you have 3 carbons from propane, 3 carbons in carbon dioxide. You have 8 hydrogens in propane, and you got 8 hydrogens in the form of water. Okay. And then you got 10 oxygens as oxygen, elemental oxygen, but you got 6 oxygens in carbon dioxide and 4 in water. So the oxygens are balanced. So everybody's balanced. Now, what does that mean? That ratio is important. Balancing equations, especially when you get into the next chapter, are going to be important in the following chapters because we're going to use that to be able to do calculations. What this says is that one molecule of propane requires 5 molecules of oxygen to give me 3 molecules of carbon dioxide and 4 molecules of water. So the ratio, and that's a ratio. The ratio between the propane and oxygen is 1 to 5. So remember when we were doing conversion factors back with units of metric to English, and we had 1 inch is equal to 2.54 centimeters. That ratio I can write with inch in the numerator or inch in the denominator. I can use that same principle here, saying that I have a ratio of 1 propane in the numerator, 5 oxygen to the denominator. And I can write it like that, or I can invert it, put 5 oxygen to the numerator, 1 propane in the denominator. I will be using that conversion factor down the road when I start to do calculations, because later down the road, I could get a question like, all right, if I have 5 grams of propane, how many grams of oxygen do I need? Question mark. Okay. Well, there's a couple of steps in between, but one of the steps is that ratio of 1 to 5 between propane and oxygen. So it's important that we learn how to balance chemical equations, okay? Because we're going to be using them later on. Any questions about this so far? Yeah. All right. Well, let us continue. So this is combustion reaction. Combustion of hydrocarbons requires oxygen. The only 2 products are carbon dioxide and water. Balance them by carbon, hydrogen, and then oxygen. And that's what this slide does. This is a summation of what I just finished talking about. Now, the acid-base reaction, the neutralization reaction. We have an acid, which HA in general form, and then we have a base, M, which is some metal, and the hydroxide to always give us water, and then the corresponding salt, Ma, which the M is the metal from the base, and the A is the anion from the acid, okay? So here we have a classic example of an acid-base reaction. We have HCl, if you recall, it's one of the strong acids. We have H written first, okay? Now let me ask you a question. Looking at the general equation for an acid-base reaction, change the color here a little bit. We have 1 proton reacting with 1 hydroxide to give me how many waters?
We give you 1 water.
Exactly. And so if I had 10 billion protons, I need 10 billion hydroxides to give me 10 billion waters, okay? Because the ratio is a 1 to 1. All right. Now, with that in mind, and I'm looking at this reaction here, it's barium hydroxide. And we know there's 2 hydroxides here. So what does that infer? That how many protons do I need? I'm only getting 1 proton the way that equation is written now with HCl. But what does that infer? How many protons would I need to neutralize those two hydroxides?
You would need 2.
Exactly. And so I can very quickly put a 2 there, okay? Because I know that I need 2 protons to neutralize those 2 hydroxides, okay? Therefore, I also know that when I get a proton and a hydroxide together, I'm going to make a water because we're neutralizing it. But since I started with 2 protons and 2 hydroxides, how many waters am I going to make?
You'll make 2 waters.
Yeah, exactly. You're going to make 2 waters, okay? And so I got 2 H2Os. I can very quickly write that. So what I'm showing you here is how to balance acid-base reactions, and that is you follow the protons and the hydroxides, okay? Now, what you got left is the barium. Now, before you put them together, my suggestion is you put them first in ionic form like we've been doing before, okay? Because that way that assures me that I put them together in the correct ratio. And I know barium has a +2 charge because 2 reasons. One, it's in group 2, okay? There's two valence electrons, so when it becomes ionic, it's a metal, it's going to lose those 2 valence electrons, okay? So that, I know that. Second, the other way to verify that is looking at the hydroxides. I know that the hydroxides, based on the polyatomic table, each have a -1 charge. And there's 2 of them in barium hydroxide. So that infers that barium must be a +2. Because remember, when we put them together to make compounds, to make the formula, we have to put them together such that we have enough positives and enough negatives to cancel them each other out, okay? Now, the A part from the general equation in this case is the chloride. And so the chloride, I know, will have a -1 charge. Again, why do I know that? Well, because it's in group 7, the chlorine is, when it becomes ionic, or specifically anion, it picks up 1 electron. Group 7 has 7 valence electrons. It's going to pick up 1 electron to fulfill that octet. So group 7 will always have a -1 charge, okay? Now, that means that I need 2 chlorides for each barium ion, right? It stands to reason. So the formula that I can put together will be simply barium Cl2, okay? And I put a 2 there for my protons, and I'm going to make 2 waters, and I'm going to make the formula BaCl2. Now, how do I know what to put AQ? How do I know that barium chloride is its physical state is AQ? What tool do you have? Okay. What tool do you have in hand to verify that barium chloride, its physical state should be aqueous? Exactly. Rebecca answered it. The solubility rules, because I can find the solubility rules of barium chloride. I'll find it that all the halides are soluble, with the exception of a few, and barium's not one of them. So it would be aqueous. And by default, in this scenario, everything balances out. I have 2 hydrogens coming from the hydrochloric acid. I have 2 hydrogens coming from the hydroxide, okay? So I got a total of 4 hydrogens on the reactant side. On the product side, I got 4 hydrogens all in water form. So my hydrogens are balanced. My chlorides, I got 2 coming from hydrochloric acid, HCl, and then I got 2 in barium chloride. So chlorides are balanced. I look at barium. Barium. I got 1 barium on the reactant side, 1 barium on product side. So barium's happy. With respect to oxygens, those are the only ones I got left. I have 2 oxygens in the form of the hydroxide in barium hydroxide, and I got 2 oxygens in the form of water. So everybody is balanced. And so my ratio here is 2 hydrochlorics required for 1 barium hydroxide. Okay, let me ask you a question. If I have, let me clear this up a little bit, which is kind of introduction to what we're going to eventually get to. If I have 100 of hydrochloric acids, well, how many of the barium, if I had 100 molecules of hydrochloric acid, how many bariums would I need for this reaction to neutralize completely?
50.
Exactly, 50, because my ratio is 2 to 1. Okay, I got 2 to 1. And so I could set up, if I wanted to, until I'm comfortable with recognizing it, I can set up a ratio of 100 HCl, because I know, and I'm trying to find out how many barium hydroxides I need. And so I can set up, because I know it's a 1 barium hydroxide. Let me put this, let me make that bracket. Okay. Divided by that ratio of 2 HCl. Remember I said earlier that we call that a stoichiometric relationship between the hydroxide, the proton and the hydroxide. It's a 2 to 1. So I can put barium hydroxide in the numerator, which is the way I set it up, because when I do the math, guess what? My HCl's cancel. Just like we did back in the day when we were working with the conversion factors, not too long ago, right? We're using the same scenario. So yes, 100 divided by 2 means that I need 50 barium hydroxides if I start off with 100, okay? And this stoichiometric relationship, that ratio of 2 to 1, is true whether I do it in the lab in small gram quantity, or if I do this reaction out and have an industrial plant where I'm making tons of this. Same ratio pertains, okay? And so it's important that we learn to balance chemical equations, because if we did this calculation and we had it not balanced, there wasn't a 2 there, we would think, oh, okay, 100 HCl's, I need 100 barium hydroxide. And that's not true. It would be incorrect. Okay. Now, going through the same scenario, similar scenario, we look at the next one. We have H3PO4, which was one of the acids we talked about in the acid-base chapter. And again, here we got three hydrogens, 3 protons. The calcium hydroxide, okay, we know that's a base, there's only 2. Okay, now I'm following the hydroxides and the protons. Now, how can I balance these out? If I got 2 hydroxides and 3 protons, and I want to put them together such that they cancel each other out, neutralize each other, what can I do here?
You can have 2 of the HPO4 and then 3 of the CaOH2.
Exactly. Just like we were doing, remember we putting compounds together and we had a +2 charge and a -3 charge. We had to find a common factor, okay? And here the common factor is 6. And so that means that I would need three calcium hydroxides for every 2 phosphoric acids, because that gives me, my common factor would be 6. 6 protons, 6 hydroxides. That being the case, guess how many waters I'm going to make? If I have 6 protons and I have 6 hydroxides, how many waters am I going to make? 6, exactly. Okay, and so I'm going to make 6 waters. See, I'm following the waters. Okay, and then I'm going to make the salt. But before we do that, let's write the salts in ionic form, so to make sure we put them together correctly. We know that calcium, again, being in group 2, will have a +2 charge. Okay, and then the phosphate, it lost those 3 protons. So now it has a negative, I'm going to write it like this, so we have a -3 charge. And so here we go again. We have a similar situation here, but we find a common factor again to put these ions together. So that means we need 3, 6 would be the common factor again. We need 3 calcium ions and we need 2 phosphates. Those numbers will be the subscript for the compounds, okay? And you're going to see by doing this, by default, guess what? They balance each other. They balance themselves out. So we need 2 protons, 3 hydroxides for a total of 6 hydroxides, a total of 6 protons. It's going to give us 6 waters. And going through the exercise of first breaking the salt into the ions, so we can determine how many of each we need to put together, we come up with 3 calcium and 2 phosphate ions. So that is the formula there. And now let's go back and let me clear it up a little bit so it doesn't look so messy. We go back and verify that, in fact, we are balanced, okay? And so we go back and we check the hydrogens. I got 6 hydrogens coming from phosphoric acid. And how many are coming from the hydroxide? 6. So I got a total of 12 hydrogens. I look to the right, I got 12 hydrogens in the form of water. So hydrogens are happy, okay? The oxygens, I got 8 coming from the phosphate, and again, 6 coming from the calcium hydroxide. So 8, wouldn't that be 14? I got, oh, excuse me, I'm adding wrong. 8 and 6, yeah, 14. And so I checked my calcium phosphate, that's 8, and 6 from hot water. Guess what? My oxygens are balanced, 14. Okay. I got 3 calciums on the left, 3 on the right, 2 phosphorus on the left, 2 on the right. Everybody's balanced. Okay. Everybody's happy. Now, so our ratio between the phosphoric acid and the calcium hydroxide, aka TUMS, by the way, is a 2-to-3 ratio. And we end up making 6 molecules of water. It's quite a bit of water is being generated. Why? Because we had quite a bit of protons to neutralize. All right. And so with respect to acid-base reactions, recognize that you have an acid and a base, and the product that you make is always water, okay? And then the corresponding anion and cation form the salt, put the salt to get first, write the ions for the salt before you put them together to make sure you put them together in the right ratio. And if you follow the protons in the base, everything, as far as balancing, everything should just fall in place and just come along and balance itself out. Okay? Any questions about this? Acid-base reaction? Okay. All right, which brings us to the single replacement reaction. All right. So if we look again at that general reaction, we have a metal, M, in elemental form. And then we have another metal, but it's an ionic form. It's a compound with something with X, whatever X may be. And we, in effect, exchange places. So now the metal, which was in elemental form, now is in ionic form. And the metal A that was in ionic form goes to elemental form. Classic example of this would be plating. I'm sure you have maybe some jewelry or a car that has chrome plating. That's what this is, basically. We're taking a metal in ionic form and we're plating it onto a surface to give you the chrome, or to give you the gold color, or to give you whatever metal you're looking for. Okay. Now, we use the activity series. Okay, and it's pretty straightforward as far as asking yourself a couple of questions. First question to ask yourself: of the metals, regardless of their elemental form or ionic form, of the metals, which one is the most reactive form? Metal. Okay, so you identify the most reactive metal first. Then the second question is you ask, is the most reactive metal already in ionic form? If the most reactive metal already is in ionic form, there's no reaction. If it's not in ionic form, then there's a reaction that proceeds. Okay, you exchange the partners. All right, we'll get some examples here in a moment. So here's the activity series. You can see that lithium, the ones highlighted in white. What happens with these guys in white when they touch water? I mean, they literally just touch water. So I can take the example of lithium plus H2O. Oh. So lithium represents from lithium to sodium. They very quickly react with water to form lithium hydroxide. They actually make a base. And then the other thing they make is hydrogen gas, H2. Okay, I haven't balanced it, but those are the two products. And those are the ones that are highlighted in white here, the bold ones. They're very reactive. The other metals, when they react, and all the way up to hydrogen, so from magnesium up to lead, in order to get those guys to react, we need a little more aggressive conditions. And we generally could react them with a little bit of hydrochloric acid. Okay. And that gives us the metal chloride plus hydrogen gas again. Okay. And that's going from magnesium up to lead. They require a lot more aggressive conditions in order for them to react. And that's why normally, for example, iron, Fe, our bridges are breaking down throughout the U.S. because we're getting a lot of acid rain. We call that acid rain. The rainwater is pretty acidic, and they react, and that acidity of the water, the protons in the water in the rain, react with the metal of the bridges over time and break it down. And one of the products is gas and then the salt. Okay. For gold, copper, anything above hydrogen, they require a lot. They need things like nitric acid and sulfuric acid, and other stronger acids to get them to react, which is good because copper generally is pretty much unreactive, which is a good thing because you don't want the water in your copper pipes at home to be reacting and, dissolving the copper. All right, so that's generally the case. So let us one way that they describe it is that the most reactive metal wants to be in ionic form. Okay, it needs to be in a compound form with whatever anion it is. And so if it's not, then reaction proceeds. So that's another way to look at it. Let's clear this up. All right, so we check the activity series, and then we determine whether the most reactive metal is in ionic form, and if it's not, then proceeds. And then we obviously we're going to put the states for the products, either solid, liquid, gas, or aqueous. All right, so let's try one. Okay, we have this reaction here where we have zinc nitrate reacting with sodium metal. So we first identify the metals, obviously, right? Regardless of them being ionic or being in elemental form. So we're comparing zinc versus sodium. We go to the activity series, find sodium, and we find zinc. And we can see from the activity series that sodium is a lot more reactive than zinc. Okay, so that means that they're going to change partners. So zinc, which is in a plus two state, will become the zinc metal. And so I can very quickly make zinc, put that down, it's going to be solid, right? Now the sodium, which has a zero charge, here's the thing to remember. All the elements have a zero charge. Remember why? Because everybody had the same number of protons and same number of electrons. So sodium right now is in a zero state. When it becomes ionic, because it's group 1, it's going to be a +1 state, okay? And nitrate is a -1. Now, how do I know that? Two ways. One, the polyatomic table, polyatomic ion table tells me that NO3 has a -1 charge, okay? Second, maybe I don't have the table with me, but I do know that zinc always has a +2 charge. And there's 2 nitrates attached to zinc nitrate. That infers that zinc must be a +2. And because there's a 2 in the parentheses, that also tells me that each nitrate has to be a -1. Okay? All right, so those are the products I'm going to be getting. Okay, I can know that I just need 1 sodium and 1 nitrate. Okay, then I got to balance them out. Okay, so let's write the equation. I know I got a 1 sodium and 1 nitrate. It's a 1-to-1, so I can write the formula as NaNO3. Okay, zinc, I don't know, it's a solid. We had a slide a few chapters back that listed how many liquids of the 118, only 2 were 118 elements, only 2 were liquids. We had about a dozen or so gases, and the rest were metals. Zinc is a solid, solid, not metals. The rest were solid, right? So zinc is a solid. Now, I don't know about sodium nitrate. I use the solubility rules. If I go in there, the fact that I got sodium written first, that's part of the big 4. Any sodium automatically soluble. Okay, so I got that worked out. I got aqueous for sodium nitrate and solid for zinc. Now, how do I balance this out? Well, here, follow the polyatomic ions. Okay, so I can see that I started off with 2 polyatomic ions, nitrate ions, to begin with. I ended up with 1. And so I can very quickly put a 2 in front of sodium nitrate. Okay, that takes care of my nitrates. Okay, but it kicked up my sodium. All right, no problem. All you got to do is put a 2 in front of sodium metal and then go back and check. All right, I got 1 zinc as a reactant, 1 zinc as a product. I got 2 nitrates as a reactant and 2 nitrates in the form of sodium nitrate. So that's balanced. I got 2 sodiums and 2 sodiums on both sides. So by following the polyatomic ions, I'm able to balance this. Okay, and so now I have a balanced chemical equation. Okay, and I know that sodium nitrate is soluble, it's aqueous. Okay, because why is that? If I go to the solubility rules and I look at number 1 in that column, in the soluble column, the big 4 there, I talked about those: lithium, sodium, potassium, and ammonium cations. Whatever the anion is, doesn't make a difference what it is, it's always soluble. So the fact that we got sodium right up front tells you it is soluble, therefore it's aqueous. Okay. And then here's the ratio 1 to 2. Recognize the ratio once you balance it, because you could be given a problem like this and then later on be asked, well, how much zinc can we make if we start off with 10 grams of zinc nitrate? Things like that. Okay. All right. So obviously the sodium wouldn't be written with 2 nitrates because, again, sodium is in group 1A. Only has 1 valence electron. Will always have a +1. Okay. And so to summarize these, I will have some more examples here in a moment, is when you look at a single replacement reaction, and you can tell you're going to deal with a single replacement reaction because one of the reactants is always an element, in this case, sodium. Okay. And so you look at these 2 reactants, look at the metals, determine who's the most reactive. Once you determine who's most reactive, ask the question, is the most reactive metal in ionic form? In other words, is it a compound? If it's no, then reaction proceeds. If the answer is yes, then there's no reaction because the most reactive metal is already in the most stable state. It's a function of stability as far as the most reactive metal. It wants to be in the most reactive state. And the most reactive state is in an ionic compound form. Okay? Take a look at this one. We have strontium bromide and aluminum. Okay, so we need to first find and determine who's more reactive. So we have aluminum sitting there, and we have strontium bromide. Okay, and so here, strontium Sr is a lot more reactive than aluminum. Okay, then the second question is, well, is the most reactive metal already in its most stable state, which is the compound? And the answer is yes. Therefore, we have here no reaction. Okay? See how that works? Now, what does that mean? That means that the reverse would work. Okay? If we reverse the scenario where we have instead of aluminum, maybe we have strontium metal. reacting with, we'll go ahead and use aluminum bromide. Okay. And maybe you're given that scenario. Same questions. All right. Who's more reactive? Strontium is more reactive. Okay. Second question, is the most reactive already in the compound form for that reaction I just wrote? The answer is no. And so, yes, you would get a reaction and you would end up with aluminum metal, okay, because you're exchanging places, okay. And then you're gonna have strontium and bromide together, but let's write the ions first. So make sure that we put them together correctly. How do I know that strontium is a +2? Okay, we know that because strontium is a group 2 element. And we know that the chlorides, or in this case, the bromides, are -1. Okay, so that means that I'm going to need 2 bromides for every strontium that I put together. Okay, so that being the case, that means that my formula would be SR2BR2. Okay, and you got to balance that out. How would I balance that out? Anybody have any idea? Is the equation I just wrote out, is that balanced? No, not at all, right? Strontium is balanced, aluminum is balanced, but I got 3 bromides on the left, 2 on the right. What can I do? Anybody want to give it a shot?
You would need 2 of the aluminum bromides and 1 of the strontium. Or I'm sorry, 3 of the strontium. Wait, no.
Yeah. How about
6.
what if we try 2 of that and 3 of that?
Okay, yeah, that works.
Where that works, okay. And so, but then what happened to my strontium? It went up, right? So that means now I got to go back and put 3 there, right? But then my aluminum is at 2, so I go back to aluminum and I put 2 there. Okay, how's that look? Does that look balanced? Yeah, I got 3 strontium on the left, 3 on the right. I got 2 aluminum on the left, 2 on the right. I got 6 bromides on the left and 6 on the right. Oh, we're balanced. Mother Nature's happy. Okay. And so the whole exercise here was twofold. One, if you get no reaction, then to demonstrate, then the opposite will be, yes, you would get reaction. And then obviously go through an exercise to balance it out. Okay. Unfortunately, here in this one, it's basically play with the numbers. You know, let's try a 2 here, see if that works. And when you're balancing those type of equations, all balancing equations, you add a number to the product side, then that makes you have to go back to the reactant side, and you go back and forth until you got the right ratio. The thing to remember is that if you get everything balanced, to bring it down to the lowest, like the term they use in mathematics, bring it down to the lowest terms, okay? Because let's say you're balancing this out and you come up with 6 of these, okay? And 4 of these, and 4 of these, put it in parentheses for right now, and 6 of these. Well, if you go through the scenario of determining if they're balanced with those numbers in parentheses, yes, they are. However, those are all divisible by 2 and bring it down to the lowest term. So the numbers that are not in parentheses are the numbers that are brought down to the lowest terms. So If you do that and you have high numbers, the last thing to check to make sure you are down to the lowest whole numbers in the lowest terms. No fractions here. Remember that. No fractions. Always whole numbers. All right. Well, let us continue. All right. So, okay. Here we have one where you have the question. Now, this time it's a little bit tricky, but let's go back to the activity. What we're going to do here is compare aluminum with hydrogen. Okay. Now, we go back to the table, activity series, I should say. We find aluminum, which is right there, and then we find hydrogen. Okay. And we ask the same question, which is more reactive, aluminum or hydrogen? It's just that the hydrogen is in the form of H+, a proton. Okay. And so the answer is aluminum is more reactive. For that example, we just were shown here. All right. That means that, yes, this reaction will proceed. Okay. Because the most reactive metal here is aluminum relative to hydrogen. Granted, hydrogen is not a metal, but relative because hydrogen is our reference point. And hydrogen, its elemental form will either be in the form of H2 or the proton or water. And I'll give an example on how that will be true. I'll show you. Anyway, the reaction is yes, and you will get exchange places because now the aluminum is replacing the position of the proton to give you aluminum chloride. And the proton, now in the ionic form of hydrogen, goes on to create hydrogen gas. Okay. Now, let me think of, all right. What if you had this reaction where you had copper to chloride plus hydrogen gas? What do you think? Would that reaction proceed? And given the activity series that you have? Okay, well, you asked the same questions. Is which you're comparing here in this case, because you're dealing with hydrogen, you're comparing hydrogen with copper. So who is more reactive, hydrogen or copper? Yeah, let's go back one. Hydrogen, exactly. Because hydrogen is right below copper. And so technically, hydrogen is the more reactive than the copper metal. Then the second question is the most reactive in ionic form. And the answer here is no, because the most reactive hydrogen is in elemental form. So guess what happens? We create hydrochloric acid plus copper goes back to copper metal. Okay. And of course, we got to balance it. So that would be probably two of that. I think that balances out. Okay. So that would be using the activity series and using this hydrogen if you're given a hydrogen example. And we're keeping in mind that this, you know, if we look at well, that wouldn't work. I was trying to think of another example. Okay, so here's an extreme example of using hydrogen and metals that are more less reactive than hydrogen. Hydrogen, again, is the reference point, and hydrogen, and that's why they put hydrogen in parentheses for just the letter, the symbol H, because it could be either in the form of H2 or H plus or water. Okay, because if you look at the metals and you did a comparison, you said, okay, sodium plus H2O. Question is, would that react? And maybe you didn't know that sodium metal was highlighted in that series. But you asked the question again, who's more reactive, hydrogen in the form of water or sodium? And sodium is very, very, very soluble. So yes, this reaction would very more reactive than hydrogen based on the activity series. Therefore, this reaction definitely would happen. Okay. And if, like I said, you would get sodium hydroxide and H2, because you are single replacing. You're replacing the sodium with the hydrogen, which is in ionic form as a form of water. So that creates hydrogen, displaces the hydrogen, and puts it back into the elemental form as H2. Okay, see how that works? All right, so let us continue. All right, of course, the states, we know H2 is a gas. I forgot about this. And aluminum chloride, again, we use the solubility rules to determine that, yes, it's soluble in solutions, therefore AQ. Okay. Totally balanced out completely. It gives us 2:6 to 2:3 ratio. All right. This flow chart kind of breaks it down for you for single replacement reaction. Okay. Find the most reactive metal on the activity series. Okay. Metal / hydrogen. Okay. In case there's hydrogen involved, either in the form of proton or water. And then if it's in salt form or is it in a compound already, if it's yes, the answer is yes, then there's no reaction. If the answer is no, then you have a reaction and you exchange the metal and the metals. Okay, and then balance them out. Obviously, write the new salts in ionic form so you can put them together correctly in the right ratio. Okay. Now, when it comes to double replacement reactions, it's all related to the solubility rules. And I want to just go over that fairly quickly again, so make sure that we are on the same boat. Okay. So on the periodic table, you have the solubility rules. We have two columns here. We have the column on the left, which is the soluble column. Okay. And then we have the column on the right, which is the insoluble column. Now, some of these tables, this table is labeled numbers in the columns 1, 2, 3, 4, 5, and it continues at 6, 7, 8. Some tables start again with 1 for the carbonate. Okay, let's talk about the insoluble column first. All right. Now, with respect to 6, 7, and 8, these are the anions. So any compound that is bonded to these three anions here, the carbonate, the chromate, and the phosphate are insoluble, okay? Insoluble, except if those are bonded to the big four. See how that works? And so there's like 10 billion carbonate compounds out there, all insoluble, except that if they're bonded to lithium, sodium, potassium, or ammonium, then they're soluble. And the same is true for the chromates, and the same is true for the sulfates, okay? Now, with respect to the sulfides, 100% of the time, they are insoluble except 7 examples. And those 7 examples, again, are those 4 plus calcium, strontium, and barium. When the sulfide ions are bonded to those 7 only are soluble, classified as soluble, which makes them strong electrolytes. Remember that, okay? Otherwise, any sulfide that you see, and they're not part of the 7 here, insoluble, okay? Same is true with the hydroxide. Hydroxide, 100% of the time insoluble except for those 4, or bonded to calcium, barium, or strontium. So again, with the hydroxides, there's only 7 examples that are soluble hydroxide compounds. Everything else is insoluble, okay? With respect to the soluble column, like I stated, number 1, the big 4, regardless of what the anion is, regardless of what it is always soluble whenever you see lithium, sodium, potassium, or ammonium cations, regardless of what the anion is, okay? The same is true with any acetate anion or any nitrate anion. And so regardless of what the cation is, if you see copper acetate, lead acetate, or nitrate, okay, always soluble. The halides, 100% of the time, they are soluble, except for only 3. When you see it with lead, mercury, or silver halide, X being chloride, bromide, and iodide. In fact, we use that property right there to identify the halides, because they tend to have a little bit different color, the chloride, silver halide, silver chloride, silver bromide, silver iodide, slightly different color. We can distinguish what halide we're dealing with, okay? And so all the chlorides are soluble except for those 3. And then again, with the sulfates, 100% soluble except for 5. So calcium sulfate, strontium sulfate, barium sulfate, silver sulfate, and lead sulfate. Only those 5 are insoluble, okay? All the other sulfates are 100% of the time soluble, regardless of the cation, except for those 5. And understanding these solubility rules, that is what drives the double replacement reactions, okay? Because if you have a positive reaction, you would get a solid, which is driven by the solubility rule. So in this case, you got AX and BY. Both of them are soluble and therefore aqueous. You mix them together. If one of the products is insoluble, then you get a solid material. And we denote that based on the solubility rules by the letter S, and you get a precipitate, okay? A classic example, you may already familiar with this, is milk of magnesia. Milk of magnesia is a cloudy solution. You pour some into a glass, you see it cloudy. And if you let it settle there for a while, all that material will settle because the magnesium hydroxides are mostly insoluble. So they will settle. So what do you normally do? You shake it up to get it form an emulsion and kind of mix things up a little bit, and then you drink it. Okay, so that's what they're talking about, a precipitate. It solid forms when it's insoluble. Okay. All right. So solid forms, reaction proceeds. No solid form for any of the products, any of the new products, no reaction. Notice what happened. The AX now becomes AY. The BX now becomes BX. The BY becomes BX, excuse me. They just exchanged the anions and the cations. And then you look at the solubility to see who's soluble, who's not. Okay? And we went over the solubility rules. All right, so we look at here. My suggestion is that one, you write all the products, all the reactants in ionic form first, so that making sure that you put them together correctly in the right ratio. And so everything's, all the reactants here are ions. And so you know you're going to flip the partners over. So barium is going to now be complex or bonded with sulfate, and magnesium will be bonded with the nitrates. So I would write new products in ionic form very quickly so I can check. So barium, I know that it will have a +2 charge. Okay. How do I know that? Well, group 2A element will lose 2 electrons. Also, I also know that the nitrates is bonded to each have a -1 charge. There's 2 of them, so that infers that I must have a +2 in barium. Okay. Magnesium. So the new partner that barium will hook up with would be the sulfate. That I need to go to the polyatomic ion table, and it will tell me that the sulfates have a -2. But if I didn't know that, the partner it has now, the magnesium, what do I know about magnesium? It's a plus. It's a group 2 element. So it's a +2 ion. So therefore that infers the sulfate must be a -2. Okay. And so those are the new partners. And now do the other one. You got magnesium, which we know is a +2. Okay. And the nitrates is what we just talked about. We know that each one is a -1 charge. Okay. So those are the new products that we'll be making. Okay. So I can see from the ions that I wrote that the barium and the sulfate will come together 1-to-1 because there's a +2 and a -2. The magnesium is a +2 and the nitrates are a -1. So that tells me I needed 2 nitrates to come together with the magnesium. Okay. So that information here now has told me the correct ratio to put them together to write the formulas for the products. While I'm here, I go ahead and look at the solubility. The barium sulfate, I go to the sulfate on the solubility rules, it's number 5, and it tells me normally the sulfates are soluble, except for those 5: calcium, strontium, barium, silver, and lead. Guess what? I got barium here. So what does that tell me? That tells me that I'm going to have a solid once I put them together, so I can very quickly put that S in there once I put together the formula, because I know that combination is insoluble. All right, I look at the magnesium nitrate now. Okay, find the nitrate, number 3 in the soluble column. There's no exceptions there. Nitrate, regardless of what it's bonded to, is soluble. Okay. Therefore, that tells me that I'm going to be using the AQ when I finally put these together as a formula. So by breaking them down into ions, that assures me that I'm going to put them back together with the correct ratio. Then secondly, looking at the solubility of each one, each new product that it made, whether it's soluble or insoluble, I can now give it the physical state. And already I know that I have a positive reaction because the barium sulfate is soluble. Okay, so I've got all that information before I even write the equation out, and I can write the equation out with that information. Now, fortunately here, when we do double replacement reactions, anytime you see polyatomic ions, when you work to balance them, my suggestion is follow the polyatomic ions. But in this scenario, the fact that we're dealing with barium +2 and magnesium +2, by default, this is a balanced chemical reaction. Okay, you see for yourself. You got one barium on the left side, one barium on the right side. I got 2 nitrates on the left side, and guess what? I got 2 nitrates on the right side. Okay. I got 1 magnesium on the left, 1 magnesium on the right, 1 sulfate on the left, 1 sulfate on the right. Just by default, this thing just balanced out. Okay. All right, so we get a positive reaction when we combine barium nitrate and magnesium sulfate. All right. All right, we'll do another one. Now, we can do the same scenario, and I recommend breaking the new products down initially into ions so you until you're more comfortable with it. Eventually, you get to the point that you look at the products, you look at the reactants, and I just, just look at the fact that you see lead, that's a good indication that you might get an insoluble product. And then, so there's lead, and the other reactant is the iodide, okay? And so looking at the solubility rules, the halides normally are soluble, except when you're dealing with silver, mercury, lead, and we're dealing with lead here. So pretty much you're going to get a positive reaction. Break it down into which lead are we using here? Anybody tell me? What's the oxidation number or the charge of lead nitrate?
Is it going to be +2?
Got it. Because we know that the nitrates are all -1, and there's 2 of them. So we're using lead 2 nitrate. Okay. All right. So you can, that tells you that I'm going to need 2 iodides, because we know that each iodide has a -1. So the formula for the lead iodide would be PbI2. And we know it's solid because of the solubility rules. And then the other partner, which is potassium and nitrate, the fact that you see potassium, just part of the big 4 in number 1 of the solubility column, of the soluble column, automatically, you know, it's soluble and therefore aqueous. Okay. As far as this, again, if you follow the nitrates, follow the polyatomic, I should say, ions, like the nitrate, if you follow that and balance those first, the rest just fall into place as far as balancing the chemical equation. All right, so let's clear this up here a little bit. All right, same thing here is we got silver nitrate and we got barium chloride, both soluble, but we got a halide chloride, we got silver, We got a combination here. It's I'm willing to bet it will be, we got the silver there, we got the chloride. All right, look at down here. Now, silver X, in this case, the chloride tells you they're insoluble. So yes, we're gonna have an insoluble solid product here. We have a reaction, okay, because silver chloride is insoluble. And so again, break them into ions as far as the new products that you're making so you can put them together in the right ratio. And you can see that by default, almost by default, we just need to put it through and we got everything balanced out. Okay. Some of these equations, as far as balancing is concerned, they're not going to be, they can get pretty crazy as far as balancing, but no, we're not, I'm not going to give you anything far out there, outlandish as far as having to balance it. It'll be pretty straightforward. Okay, so these type of reactions that we talked about, they're classified as what we call redox reaction. What that means is it's a term that has been put together from two terms. Oxidation is one term, okay? And that is loss of electrons. So anything that loses electrons has undergone oxidation, okay? Now, anything that gains electrons undergoes what we call reduction, okay? So oxidation is loss of electrons. A lot of people use the X for exit the building, so to speak. Electrons leaving. Oxidation, loss of electrons. Reduction, R for returning. The electrons are gaining or being picked back up. They're gaining electrons. They combine the terms, the RE from reduction and RED and the OX from oxidation, hence the term redox. And a lot of these reactions that we talked about are under the umbrella of a redox reaction. Because what's happening is that one of the reactants will lose electrons while the other reactant will gain electrons. In fact, redox reactions occur simultaneously. They don't occur separately. They're the yin and the yang of reactions. What happens to one, the opposite happens to the other. Now, another way to look at it is that the element's charge or oxidation number goes down when it undergoes reduction, or its oxidation number goes up when it undergoes oxidation, okay? And what I mean by going up, we're talking about in terms of like value, mathematical value. It goes from a 0 to a plus number, positive number, or it goes from a 0 to a negative number, that's a negative number. That's what they're talking about here. We'll do some examples here in a second. Okay. Let's erase this. All right. Quick review on oxidation numbers. We know that group 1A has a +1, group 2A +2, group 3A is a +3. Now, group 4, very unusual. I did send an email concerning carbon and carbides. Group 4, they're very unique in that there's 4 valence electrons, okay? And so that means that the elements in group 4 can either gain 4 electrons or lose 4 electrons, or any combination thereof. And carbides are kind of unique. The carbides can gain 1, can gain 2, kind of unique. So we never really talk about it here at Chem 130 level. So with respect to the nomenclature, if you did get a carbide question and you got it wrong, let me know and I'll give you credit for it. Carbides could be very complex as far as making compounds. It's not a straightforward group 1, group 2 charge. Okay, I sent an email to that effect concerning nomenclature exam. So if you did get a carbide question, you got it wrong. If you got it right, fantastic. If you did not, let me know. I'll give you credit for it. So anyway, their charge for group 4 can vary from a -4 to a +4. And again, once we get past that group, then we start gaining electrons. We're into the realm of the nonmetals. They're close to the noble gases. It's easier for them to gain electrons than it is to lose them. So group 5 is going to pick up 3 electrons, group 6, 2, group 7, 1 electron. Okay. That's also as a guide to tell you how many bonds they can make. Group 5 elements, when they make a bond to make a neutral compound, will make it the maximum 3 bonds. Ammonia, NH3, 3 bonds. Group 6, those elements at the maximum, they can make 2 bonds and remain neutral in charge. Water, 2 bonds in water, H2O. And then you got group 7 with a -1 charge. That also tells you the maximum bonds it could make is 1. Hence hydrochloric acid, HCl, 1 bond. Okay, and still remain a neutral element. So not only does that tell you how many electrons it will gain, but it also helps you with how many bonds it can make. All right, and of course we know group 8, valence shell is happy, not gonna happen. And then we talked about the sweet 16 as far as group 1, group 2A, those are 12 elements there, but then I also gave you 4 more: zinc, cadmium, silver, and aluminum. Those are always have a constant oxidation number. Okay, so as I spoke about losing electrons, that's when the charge goes up. So if we look at this example where you have copper and it reacts, and guess what? It went from a 0 charge to a +2 charge. All right, and so it gave up 2 electrons. That is called oxidation. So its charge went from 0 to a +2. Okay, so solid copper is what is being oxidized here. Being that copper, in this case, solid copper is what's being oxidized, it is also given the name as the reducing agent, because solid copper offers the electrons for another species to come in to pick up. So it's an agent for those undergoing reduction. Okay, so what is oxidized is called the reducing agent. Sulfur here, for example, gains 2 electrons. Okay, and so it underwent reduction, and so its charge goes down in value. It went from a 0 to a negative value, -2. Okay, that had nothing to do with how many electrons, or it just gained a negative value. Okay, so it went down. So in this case, solid sulfur is reduced, and it being reduced is then classified as the oxidizing agent. Okay, so if you undergo reduction, you are the oxidizing agent. If you undergo oxidation, you are the reducing agent. Okay. So the one thing about redox reactions, you can't have one without the other, always occurring simultaneously. And what is being reduced and oxidized has nothing to do with the reactants. It has to do, always has to do with the reactants, not the products. Whatever happened to the reactants, that's what created the products, right? So your answer is, as far as what is reduced, your answer will always be a reactant, not one of the products. Okay, so let's do some examples. For example, we have this one here. We have copper 2 ion in the process of interacting with iron. Okay, and so copper went from a +2 state to a zero state. Okay, to do that, it got reduced. Okay, it gained 2 electrons. Iron went from a 0 to a +2 state. So in that scenario, it underwent oxidation because it lost 2 electrons, which copper picked up. Therefore, iron, solid iron, is what is oxidized, so it is the reducing agent. And copper 2 ion is what is reduced, so it is the oxidizing agent. Okay. Here's some real life example. This is copper, excuse me, not copper, cobalt 3 nitrate. It's an actual compound utilized a lot for chemotherapy. But this reaction, cobalt in the process of platinum undergoes the following reaction. Cobalt went from a +3 state because there's 3 nitrates around it, and we know the nitrates each are -1. So that means that cobalt in this state has a +3 oxidation state. But this is a single replacement reaction. And so cobalt went from a +3 to a 0. Okay. Platinum went from a 0 state to a +3. So in order to do that, it lost electrons. So it underwent reduction. Cobalt 3 underwent reduction because it picked up 3 electrons, 3 negative charge electrons, because it started with a +3. And by picking up 3 electrons, it becomes a 0 charge. And so what is oxidized is the platinum metal, which makes it the reducing agent. And what it is reduced is the cobalt 3 nitrate, the whole compound, not just the cobalt. You got to list the whole compound. The cobalt 3 nitrate is what is reduced, and it is the oxidizing agent. And we know that that's cobalt 3, Roman number 3 nitrate, because we know the nitrates each are -1, and there's 3 of them. Okay. So there's a lot of YouTubes concerning, not a lot, but the ones we have, the one I have here, I record, also Dr. Kim's and the course website. But again, you can go on YouTube and do a search for these particular topics, and you'll find dozens of YouTubes of other instructors that have presented a topic. By all means, look at them as, sometimes listening to this topic in a different manner could be quite instructive, so do what you got to do so you can get these concepts. Let me summarize this, okay? So for this particular chapter, be familiar with the solubility rules, how to use them, and how to use the activity rules, okay? Don't need to memorize them. Why? Because you have the periodic table. There's no need to memorize at all whatsoever. But be familiar in how to interpret the solubility rules and the activity series, okay? Recognize and be able to balance combination reactions. Combination reactions generally are 2 elements coming together to make a compound, okay? A decomposition reaction generally is a compound that is reacted to create or generate the elements that compound was made from. So combination starts with the elements to give you a compound. Decomposition starts with a compound to give you the elements, okay? Recognize a single replacement reaction. Normally you have a metal ionic compound reacting with an elemental metal. So you may be aluminum chloride plus sodium. Okay, sodium is the element, the elemental metal. Aluminum chloride is the ionic metal. Okay, identify who's more reactive and determine who, if the one is more reactive is an ionic form, then if it's not, reaction proceeds. If it is, no reaction. Okay. Also be sure to balance it and give it the physical states. A double replacement reaction, you rely on the solubility of the product. So basically you start off with two soluble reactants, you exchange the partners, okay? And then you look at the solubility of the new products you created. If the products are all soluble, then there's no reaction. If one is insoluble, then yes, you have a reaction, positive reaction. Okay. Acid-base neutralization. Recognize that you have an acid 9 times out of 10, you got hydrogen written first, followed by whatever. And then the base, you'll find the majority of the time it'll be a compound with a hydroxide group there, okay? Because we have an acid-base reaction, the proton and the hydroxide. They always give you water, okay, all the time. So proton plus hydroxide give you water. To balance it, follow the proton, follow the hydroxides. If you got 10,000 protons, you need 10,000 hydroxides, which will give you 10,000 waters, okay? Combustion reaction, the only combustion you need to be worried about is combustion of hydrocarbons, and that is compounds that are made up of nothing but carbon and hydrogen. You combust hydrocarbons, the reactant you need is oxygen, and the only two products that you're going to make are carbon dioxide and water, okay? We balance those by first balancing the carbons, then you balance the hydrogens, and then at the end you balance the oxygens. And they balance themselves pretty readily, okay? Look at a reaction, either one of these, because a lot of these are redox reactions. Identify what is oxidized, what is reduced, and what the respective agent is. Remember, oxidation is loss of electrons. So if you look at a metal and it goes from a +3 to a 0, then it gained electrons, okay? If you look at a metal and it went from a 0 state to a +1, then it lost electrons to give that plus charge. All right. Other than that, we're done with chapter 10. Okay. And chapter 11 is extremely short. I think next Friday we will knock that out because we're a little bit pretty much ahead because next week, chapter 11, I'll knock that out. Let me stop here for a second.